Okay guys, this is a little different. I'm going to give you a quick lesson in chemistry. This is chapter 4, beginning chapter 4, talking about stoichiometry or chemical reactions. And don't let the big word stoichiometry scare you. It's kind of fun to say. You can try it, say it, stoichiometry. I don't know why it's fun to say, but it is. It's a big word. Not many people know the definition too. But it simply means the chemical reactions, and we're going to use some numbers to make those chemical reactions happen. But if you look in your book, chapter 4, there's a few things I want to point out to you, and I'll show it to you right here. Don't mind the orange in my book, just a little bit of information we needed to highlight. But right up here, you're going to see key symbols and abbreviations. That's going to help you know what we're talking about. And we'll go over those in just a second, but make sure you remember that those are there at the front of each chapter. Those are there. It's going to help you through that chapter. It'll be a big help to you, especially if you need to refer back to them to see what a symbol or what a letter means. So our book says that since chemistry is a study of matter and changes that it undergoes, a very important part of that study is chemical reactions. As a matter of fact, it's probably the most important part of chemistry that you're going to come across. And what we're going to learn here is very, very basic. It stems into way out there with chemical reactions, whether we're making something, synthesizing something, or breaking it down. And it gets very, very complicated very fast if you don't know what you're doing and if you don't build on bases and line upon line, as the Bible teaches us to. But right now, we're going to learn very basic balancing equations. That's 4.1. Now, a chemical equation, our book says, is a symbolic representation of a chemical reaction. So we see up here a symbolic representation of a chemical reaction. We'll get to what this reaction is in just a moment. Here's another or partial symbolic representation of a chemical reaction. It's only halfway written because I need to wait till we get this done in order to write this one, because it extends a little bit into it. But on every equation, every chemical equation, we have two sides. We have what we call the reactant side, and we have the products. Now this side over here, the left side, is the side that's going to be reacting together. They're the two or more things that are going to go together and produce or make the products. And so every side has a reactant side and it has a product side. Right in the middle, we have the yield sign. I have those written over here. These are our basic things that we see at the top of that page there. They're key symbols. That's a yields sign. Now, what is a yield sign? A yield sign is the same thing as saying equals, except for in chemistry, we don't use an equal sign. We use this arrow that says yield. So we get from this point to over here, yield. So why do we do that and not use an equal sign? Because we're going to get to a point where we're going to see some reversible actions, reactions, and we need to be able to tell whether it's going this way or whether it's coming back this way. So that arrow helps us determine that. And so just think of it right now. It's okay to think of that yield sign as an equal sign. These things reacting is going to equal these products. And so that's not a bad way to look at it. And then you're going to see there, right below that, right in the middle of that first column on your page, a little bit of what we talked about before, those symbols, a G, an L, an S, and an AQ. What in the world does that mean? Well, it breaks everything down into 4 different states, if you want to call it that. The gas, there's a liquid, a solid, and an aqueous solution. Aqueous solution just means a water solution. And down here, we'll get to this in just a moment. But why do we have to write these? Well, and you'll see on the equations that we have here, partial equation, G and G, gas and gas. Over here, you'll see a solid and a gas and a solid and a gas. Again, so why are those important? It's important because some elements, some molecules, some things can be in different states, and they react differently when they're in different states. And so we need to know what state it's in order to know how it's going to react. Again, this is very, very basic, but they are giving you those principles set first so you don't get confused later on down the road. Okay, so Along with all those symbols, we do see the symbol here, delta, and then yields. Now delta, or if you want that triangle looking dude, we call it delta. It means that in order for this reaction to happen, or in order for it to happen as we see it written, and this one's not like that, but in order for a reaction to happen as we see it written, that delta means heat. There are some things you just have to heat up, some things you just have to add heat to in order for it to work. Otherwise, it's just not going to happen. And so in this case, well, either one of these cases, we don't see that. But whenever you see that delta above the arrow, just know that we have to add heat. Oh, bless me. So, going on a little farther, Dalton gave us a principle. He said that atoms can neither be created nor destroyed in chemical reactions. They can only be rearranged. And so what that means is I have a marker here. If I were to set this marker on fire and burn it till it was a crispy piece of plastic, I would still have a crispy piece of plastic. The matter would still be there. Now, it wouldn't look like this, it wouldn't work like this anymore, but the matter would still be there. And so if I had an equation that said I have marker plus some O2 with combustion, I have to add some heat maybe, and I'm going to end up with some carbon and some other stuff, I still have every bit of matter that I started with. I'm not going to lose any of that. It's still there. And so that's the law of conservation of mass. Whatever I start with, I have to end with. And so you can't just say, poof, there's no more, iron, or there's no more hydrogen, or there's no more oxygen. It's all going to be there still. It may be in different forms. It may be attached to different elements or to different molecules, but it's still going to be there. And in the same way you can't get rid of, you can't just magically in an equation add something to it, to the other side. You can't just have something here and all of a sudden there's more of it on this side than what you started with. That doesn't work because it's the law of conservation of mass. We conserve that mass. Whatever we start with is what we end with. Okay, since mass is conserved, our book tells us, in chemical reactions, and atoms do not change form from one type to another, there has to be the same number of atoms on one side as there is on the other side of an equation. And so that's what we're talking about now, balancing these equations. So you can think of it like this. If we have, this is our fulcrum, and we have a scale, and we can see maybe one side is going to be heavier right now than the other side. This equation is not balanced. We need to make sure there's the same amount of Fe, or iron, on one side as there is the other. Now we can look right now and see I have Fe. Over here I have Fe3. Okay, so there's 3 irons over here and only 1 iron here. That's not a balanced equation. How do we fix that? We're going to see in just a second. Our book gives us a few hard, fast rules, steps, not really hard, fast rules, but steps to help us balance these equations. Number 1, it says write the correct formulas for the products and reactants on the appropriate side of the arrow. And we already have that done for us right now. We have Fe solid plus H2O gas is going to yield, or iron solid plus water in a gaseous state, or maybe what we may say a vapor, is going to yield iron oxide plus H2 or hydrogen gas. Now, just a quick question. Do we know what Fe3O4 is? Do we know what iron oxide is? If I had a piece of metal and I put vapor over it, or gaseous water, what's that going to be? What's that going to make? What's going to happen to that metal? It's going to, we would say it's going to rust. And so that iron oxide is simply that rust, that orangish stuff that bubbles up and peels up off there. That's what that is. That's that rust, that iron oxide. And so it tells us what we have to do. Our step 1 is to make sure we have the correct formulas. Now, not necessarily the correct number of how many of each molecule is there, but the correct formula, Fe, H2O, and this will really, what if I was writing iron oxide and I didn't write Fe3O4? What if I wrote Fe2? O4. Would that be correct? Well, no, it wouldn't be right. And we know from naming our molecules why that is the way it is, Fe2 or Fe and then O, because they're charges. I won't necessarily go into that right now because we should have already known that. If you have a question about that, we can help you with it at a different time. It's a different lesson. But it has to be Fe3O4, so we have to write out the equations correctly. Once we get that done, we're going to balance the equations by putting number coefficients in front of any one of these that we need to. Now, we're not, or can we never change any subscripted number. And why can't we do that? We just explained that, because I can't change the subscript here, just get rid of that 3, or I can't add a 3 like right here, because what that would do is it would change the molecule there, and it may not and probably would not even work in the state that it is. It doesn't make any sense. Okay, so we have to add just coefficients here. And you're going to say, oh man, we just pick numbers out of the air and stick them in there. No, there's a process to it. Look at number 3 step. Check to see if all the atoms in the equation are balanced. So let's start with this one here. Again, we have iron solid plus a gaseous H2O yields iron oxide solid plus gaseous H2. And H2, I'm going to point this out real quick because H2, a diatomic element, it always comes naturally. We find it H2. You never find just a single H. They're bonded together. An H and H are bonded together because, well, we'll get to that later on in the book. But anyway, that's why there's an H2. So what are we going to do first? Well, we're going to look for the most complicated molecule in our whole equation. What is the most complicated molecule in our equation? Well, it's, to me, and hopefully you see it too, it's kind of obvious, Fe3O4. That's the most complicated molecule that we have. And so let's start with this. I have how many oxygens in Fe3O4? All right, there's 4 oxygens, O4, there's 4 of them there. I'm gonna look back over here. That means that if I have 4 oxygens on this side, I need 4 oxygens on this side. So how can I make it 4 oxygens on this side? Well, can I just put a 4 right here? No, I can't do that. What I have to do is add the numbered coefficients, 4 there. So what this means is, instead of there just being one H2O, now one H2O molecule, which by the way, the H2O molecule looks maybe something like this. Instead of being one of those, there's going to be 4 of those. And if you could imagine it like that, now how many oxygens do I have? Well, 1, 2, 3, 4. I have 4 of them. Okay, and then in the same way that 4 is multiplied to that O, it's also going to be multiplied to that H. How many H's do I have? Well, 4 times 2 is 8. You see 1, 2, 3, 4, 5, 6, 7, 8. And so when I put this coefficient here, it means that there's that many molecules of whatever we're talking about. There's 4 molecules of water. So it gives us a total of 4 oxygens there, and I have 4 oxygens here. Now let's look at this. 4 times 2 is what? 8. So there's 8 hydrogens. We just showed that there. How many hydrogens do I have right here? Well, only 2. And so what do I need to do to make that work? I've got to multiply that by 4, because 4 times 2 is 8. So notice that I started here with the O4 went to here. And then I went from here to here. Okay, so it's kind of building on each other as I'm going back and forth, but I always start with that most complicated one. All right, so let's look here. Now I have 4 times, well, there's no subscript, no number here, so 4 times, we'll just say it's 1. 4 times 1 is 4, and then 4 oxygen here. So oxygens are balanced. I have 4 times 2 is 8 hydrogens. 4 times 2 is 8 hydrogens. That's balanced. I have 3 irons, but only 1 iron here. How do we balance that? Well, if there's only 1 here, I'm going to add a 3 here. And that will say 3 iron and 3 iron. So at this point now, is my equation balanced? Yeah, it sure is. So I can say 3 irons, 3 irons. 4 times 2 is 8 hydrogen. 4 times 2 is 8 hydrogen. 4 times 1 is 4 oxygen, and I already had 4 oxygen there. So in order to balance an equation, I have to make sure that every element, where there's iron, hydrogen, even if it's part of a molecule, every element is balanced one side or the other. All right, so let's look at this second equation. We only have it halfway written there, but if I have C4H10, C4H10 is just butane, gaseous butane, and I react it with oxygen, it's going to give us a couple things. It's going to give us CO2 in a gaseous form. Put that gap on the wrong side. And it's also going to give us water, or H2O, also in a gaseous form, or vapor at that point, but we can catch that water if we wanted to. You typically don't need to. Okay, so what do we do from here? Let me grab my other marker. Oh, there it is. So where do we go from here? What are we going to start with? Well, let's go ahead and see if, first of all, if it is balanced. I have 4 carbon and, just 1 carbon. No, it's not going to work. 10 hydrogen and 2 hydrogen. No. I have 2 oxygen and 2 oxygen. That's good. Oh, but wait. I have 2 different sets of oxygen. So I have 1, 2 oxygen, 1, 2 plus 1 makes 3 oxygen. So where are we going to start? Okay, let's start with our most complicated molecule here, and that's going to be our C4H10. All right, so I'll start with carbon. All right, so I have 4 carbon here. How many do I have here? I just have 1. So how do I get them to match? I'm going to multiply this side by 4. So now I have 4 carbon and 4 carbon. All right, so I'm on a roll. I'm doing pretty good. And now let's look at my hydrogen. Okay, I have how many hydrogen here? Well, I have 10. How many do I have here? 2. Can I get those to match anyway? I sure can. I'm just going to multiply this by 5, because 5 times 2 is 10. And so now this one, I have C4H10, C4H, well, 5 times 2 is 10. So my C's are balanced, my H's are balanced. Now I just got to balance my O's. How am I going to do that? Well, let's first see how many O's we have on each side. I have 2 on this side, and then over here I have 4 times 2 is 8, and here I have 5 times 1 is 5. 8 plus 5 is 13. Okay, so I need 13 over here. I'm going to write this down so you see. What I need is 13 over here. Now there's a problem. My problem is it's O2. Now we talked about hydrogen being a diatomic element. Oxygen is also a diatomic element. It always comes grouped or paired with another oxygen, an O2. Okay, so if I write a 13 here, I'm going to end up with 26, and that's going to mess everything up. So what do? Don't freak out here. This is a pretty simple process, but we need to see it in order to understand it. So I have 13, and we understand that if I multiply that by 2, I'm going to get 26, but I don't need 26. What I need, again, is 13. So here's what I have to do. I need to multiply by 13 over 2. And of course, from our basic algebra, we understand that the 2's will cancel. Okay? And you say, what do you mean I need to multiply by 13 over 2? I can't have a fraction in front of this. That's not going to work. And you're right, that's not going to work. And so whenever we see this, or whenever we see something like this, what we are going to do is we're going to take this 2 and we're going to multiply it by every set of molecules, every reactant, every product. So this 2, I'm going to multiply it by this here. I'm going to multiply it by this one here. When I do that, they just cancel. I'm going to multiply it by this one here. 2 times 4 now is 8. Multiply with this one here. 2 times 5 now is 10. And you see what happens now is I no longer have 13 over 2. I have 13. So I have 2 C4H10 or butane molecules. I have 13 O2. Then those are going to react and yield 8 CO2 molecules and 10 H2O molecules. All right, so let's check and make sure we're balanced. Well, let's look at our C's. 2 times 4 is 8 and 8 C's. Look at our H's. 2 times 10 is 20. Well, 10 times 2, well, that's 20. What about our O's? Well, 13 times 2 is 26. Well, 8 times 2 is 16. 10 times 1 is 10. And that 16 plus the 10 gives us a 26. And so this is balanced. Now remember what we did here, how we got to this 13 over 2. We balanced the C's, balanced the H's, and then we went over to this side and found out that we have 13 with the green numbers here, 13 O's. So I said I need 13 over here, but the problem is I had that little 2 right here. So 13 times 2 is 26. That's not what we needed. We needed 13. So if I put it at 13 over 2, and then I multiplied every product, every reactant by 2, that'll allow me to cancel that 2. And everything here gets changed, I understand that, but then that balances the equation. Those aren't easy just to see and to pick up and to say, okay, that's how we do that, but you'll have to work some like this in order to get a feel for it. Our book tells us right at the end of page 51, while a part of balancing equations is by inspection and involves trial, it does involve trial and error. You have to work at. The guidelines presented should make your approach to balancing equations more systematic rather than chaotic. Sometimes you can just look at it and tell, but use the steps. They're there to make things more systematic, a little easier for us to follow, instead of just looking at it and saying, oh, I don't know, and then giving up on it. We don't want that to happen. Use the steps, follow the steps, and although it may seem complicated at first, the more you do, walking through it, it will begin to make sense. And hopefully we'll get a grasp on balancing equations. We'll probably give some more lessons in the future on video if we need to help out with different subjects that we're having problems with. But if you have any questions, by all means let me know. You can put even a question in the comment. I'll do my best to answer from there.